In section 1.2, we're going to be basically talking about how you go about collecting data. That's really sort of the overall theme of chapter 1. It's like an introduction to concepts, but then it's also about how do you go about collecting data. In section 1.2, we talk about observational studies versus designed experiments. Again, these are basically the two broad ways that we go about collecting data. So data is either going to be collected through an observational study or through a designed experiment, one of those two. Usually it's observational studies, but lots of times there's experiments as well. So what's the difference? In research, we wish to determine how varying the amount of an explanatory variable affects the value of a response variable. So oftentimes in research, we're trying to determine if there's any kind of a relationship between two different variables. So, for example, maybe I would want to know, maybe I'm a pediatrician, and I want to know, is there a relationship between, let's say, the length of a newborn baby and the weight of a newborn baby? Is there a relationship between those two things? It seems logical that they might be, but I don't know for sure if there is. But what I would think is that maybe a shorter baby might weigh less and a longer baby might weigh more, but I don't know that. If I'm trying to determine that relationship, then one of those variables is going to have to be an explanatory variable, and one of the variables is going to have to be a response variable. For example, can I say that longer babies weigh more and shorter babies weigh less? Is that possible? Well, if I want to try to predict what a baby would weigh based on how long it is, then I am, again, looking for a relationship between those two variables. And so the explanatory variable would be the variable that is affecting the value of the response variable. So again, if I'm looking at the length and the weight, probably what I would look at is, can I explain what the weight is by using the length? So that would make the length of the baby the explanatory variable, and that would make the weight of the baby the response variable. Now, all of you've had at least college algebra to be in this course. And in college algebra, with functions, we talk about relationships between two variables. We have an independent variable, which is usually represented by the letter x, and we have a dependent variable, which is usually represented by the letter y. So if we have a linear equation like y, I'll just write it here, like y equals 2x plus 3, then x is the independent variable and y is the dependent variable. The value of y depends on x. So if I plug 7 in for x, I get a different value for y than if I plug -3 in for x. So the value of y is determined, it's dependent on what the value of x is. It kind of works the same idea as the explanatory variable and the response variable. The explanatory variable is like x. It's like the independent variable. The response variable is like y. It's like the dependent variable. So we're going to try to explain the value of the response variable by using the explanatory variable. So take a look at this example. Researchers wanted to determine whether there is an association between mobile phone use and brain tumors. To do so, 791,710 middle-aged women in the United Kingdom were followed over a period of 7 years. During this time, there were 1,261 incidences of brain tumors. The researchers compared the women who never used a mobile phone to those who used mobile phones and found no significant difference in the incidence rates of brain tumors between the two groups. And we have the source for that here. So again, what they're doing in this particular research is trying to determine if there is a relationship between cell phone use and brain tumors. So In that scenario, cell phone use is the explanatory variable, and brain tumors is the response variable. The incidence of brain tumors is the response variable. They're trying to basically say, if a person uses a cell phone more, are they more likely to get brain tumors than if they use a cell phone less? Now, in this research, they determined that there was no relationship between the two, but that's the scenario. Now, the study that's being done in this example is called an observational study. So I'll define an observational study versus a design experiment a little more clearly, but basically an observational study is a scenario where the researchers aren't introducing any factors into the research project. So what I mean by that in this particular case, the researchers were just observing how much individuals used the cell phones and how often brain tumors occurred. They didn't do anything that would cause brain tumors, either to be higher or lower. They were just observing what people naturally did in that scenario. So that makes it an observational study. Now take a look at the second example. Researchers from the United States National Toxicology Program conducted a study to address the concern that radio frequency radiation, RFR, may be associated with an increased likelihood of developing brain tumors in humans. Certainly, it is unethical to purposefully expose humans to a potential carcinogen. So rats were used instead. The researchers randomly assigned 90 rats to one of 3 possible groups. Each of the groups was housed in a reverberation chamber that allowed the rats to be exposed to the RFR. Group 1 rats served as a control and were not exposed to any RFR in their chamber. Group 2 rats were exposed to Global System for Mobile Communications, GSM, modulated RFR, and Group 3 rats were exposed to Code Division Multiple Access, CDMA, modulated RFR. Now, I don't know what any of that actually means, but they're exposing these rats to some level of radiation. So GSM and CDMA are the modifications primarily used in the United States. The rats in groups 2 and 3 were exposed to RFR using a continuous cycle of 10 minutes on, exposed, and 10 minutes off, not exposed. So 10 minutes of radiation, then 10 minutes off of radiation, 10 minutes back on, 10 minutes back off, and so on, for a total daily exposure time of about 9 hours a day, 7 days a week, for approximately 2 years. So for 2 years, they're spending 10 minutes on, 10 minutes off being exposed to radiation, these rats. Each chamber was maintained on a 12-hour light cycle with a temperature of 72 degrees Fahrenheit plus or minus 3 degrees, a humidity range of 50 plus or minus 15%, and with at least 10 air changes per hour. All rats had the same access to food and water. The researchers found low incidences of brain tumors in rats exposed to RFR for both the GSM and CDMA modification, or modulations, I should say, while there were no cases of brain tumors in the control group. However, the incidence rate was not statistically significant. So this second example is a designed experiment. Do you see the difference between the two examples? In example 1, first of all, that was looking at people, and there was no exposure by the researchers to radiation from the cell phone use, for example. So they're in example 1, they're just observing. They're not introducing the variable radiation exposure. But in example 2, the researchers are introducing radiation exposure on the rats. Now, obviously, like it said, you can't do that on people. That's unethical. I guess it's even questionable if it's ethical on rats, but definitely better than on people. Anyway, so example 1 is an observational study. Example 2 here is an experiment. In both cases, the exposure to the radiation from what would be a cell phone, although in the experiment it wasn't actually a cell phone, they were just exposing to the same kinds of radiation. But it's like cell phone radiation as the explanatory variable, and then the incidence of brain tumors as the response variable. So what is the goal of both studies? The goal of both studies is to try to see if there's an association between the cell phone radiation and brain tumors. What are the explanatory and response variables in both studies? In both studies, the explanatory variable is the cell phone radiation. We could give that the specific names listed here in the studies versus the incidence of brain tumors. So the explanatory variable is the cell phone radiation, and the response variable is the incidences of brain tumor. So again, the point of me having this all laid out here is to sort of lay out the difference between an observational study and a designed experiment. What are some differences between the studies? Well, we could list a bunch of them, but primarily the big difference is that in the first example, the researchers are not manipulating the amount of radiation that an individual is exposed to. And in the second example, the researchers are manipulating the amount of radiation that the individuals, the rats, are exposed to. So that is one of the big differences in the way those work. So let's formally define this. So an observational study measures the value of the response variable without attempting to influence the value of either the response or the explanatory variables. That is, in an observational study, the researcher observes the behavior of the individuals without trying to influence the outcome of the study. So it's very, very common research to do an observational study. You are just observing what's occurring rather than actually doing anything to manipulate. The second definition, if the researcher randomly assigns the individuals in a study to groups, intentionally manipulates the value of an explanatory variable, controls other explanatory variables at fixed values, and then records the value of the response variable for each individual, the study is a designed experiment. And so notice in that second example, it talked about that basically everything else was controlled. The amount of wake time versus dark time, so how much light, 12 hours of light, 12 hours of dark, how much food and water that the rats were able to access, all of that was controlled. The only thing that was different in the three groups of rats was whether or not they were being exposed to the different types of radiation. One group, which we call the control group, wasn't exposed to any radiation. And then we had two different kind of treatments. One group of rats was exposed to one type of radiation, whereas another group of rats was exposed to a different type of radiation, depending on the kind of cell phone, I guess, that's being used or whatever. Anyway, that is a designed experiment. They're clearly manipulating the type and amount of radiation that the rats are being exposed to. So if I were to ask you, say on a test, to explain the difference between an observational study and a design experiment, what I'm basically looking for is that in an observational study, the researcher just observes the results without manipulating any of the variables, not the explanatory variable or the response variable, either one. In a design experiment, the researchers are intentionally manipulating at least one variable to see if they can determine what the effect is on the response variable. I do want to say one thing just to be absolutely clear about it. Sometimes when I've asked that specific question on tests, I find that students have some misconceptions. In an observational study, sometimes what students says is that the researcher doesn't interact with the people being studied. And that's not necessarily true. That doesn't have to be true. It's okay for the researcher to interact with the individuals. They just aren't supposed to influence the values of the variables. So like, for example, if I wanted to determine if there's a relationship between say like blood pressure and heart attacks. If I'm doing an observational study on that, I'm going to have to interact with the individuals to get their blood pressure. So there can be an interaction, but I'm not going to be doing anything to cause a blood pressure to be high or low or normal or what have you. Other study considerations. So when we're doing a study, and this is whether or not it is an observational study or a designed experiment, either one, we have other things that we have to consider in the study and try to deal with. The first is this issue of confounding. Confounding in a study occurs when the effects of two or more explanatory variables are not separated. Therefore, any relation that may exist between an explanatory variable and the response variable may be due to some other variable or variables not accounted for in the study. So, for example, let's say on the rats example, if I'm letting one group of rats have, say, more food and water than another group of rats, and I'm not controlling that, it's possible that it could be the food that's being consumed or the water that's being consumed that might be affecting incidences of brain tumors rather than the radiation. Confounding occurs when it looks like there's maybe a relationship, but there could be other factors that we didn't consider that may actually be the cause of the relationship. So we have to be very careful and controlling about that. So a lurking variable is an explanatory variable that was not considered in a study, but that affects the value of the response variable in the study. In addition, lurking variables are typically related to explanatory variables considered in the study. So again, if there's some other variable that we didn't take into consideration in our study that may influence the value of the response variables, then that's called a lurking variable. So we might make a flaw in our study, and we might then end up with an incorrect conclusion. We think that radiation's causing brain tumors, but maybe it's actually this lurking variable that we didn't consider that's really causing the brain tumor. So we have to worry about that. We want to make sure that we take all variables into consideration. Note, observational studies do not allow the researcher to claim causation, only association. And that's a big deal. A lot of times, individuals want to be able to say, this causes that. And it may be that the explanatory variable causes the response variable. It may very well be true, but in an observational study, you can't really make that jump. Just because two things are associated, that does not necessarily mean one causes the other. I'll give you a quick example. A study was done in which the researcher looked for an association between church attendance and incarcerations, so number of individuals in jail. And so they gathered data. They went to like different towns and so on and basically determined like what church attendance was in those towns and then how many individuals in those towns were incarcerated. And they found a relationship. They found that towns that had fewer people who attended church also had fewer people who were in prison, and towns that had more people who attended church also had more people in prison. So does that mean that church attendance causes people to go to jail? I would certainly hope not. Instead, there's a lurking variable. There's a confounding that's going on in that particular study. It is interesting that there is an association, but what the study didn't take into account was the size of the town. So if it was a smaller town, there were fewer people who attended church because it's a smaller town, and there were fewer people in jail because it was a smaller town. And if it was a larger town, there were more people who attended church because it's a larger town, and there were more people in prison because it's a larger town. So the lurking variable is the size of the town that's really sort of explaining both. So there can be an association without there being a cause and effect relationship. That's the point I'm trying to make. So again, observational studies do not allow researchers to claim causation, only association. A confounding variable is an explanatory variable that was considered in a study, but whose effect cannot be distinguished from a second explanatory variable in a study. So again, we call that a confounding variable. So for example, if maybe we want to look at acceptance into a select college, as part of that, we include maybe IQ and we include high school GPA in our study. So we're looking at an individual's IQ, an individual's high school GPA, and then we're also looking at acceptance into a select college. Well, it's very, very possible that there could be some kind of a relationship between IQ and their high school GPA. So it might be that an individual with a higher IQ may have a higher GPA. It may not be true also, but it could be true. And people with a lower IQ could also have a lower GPA. Again, that may not be true, but it's possible that it could be true. Anyway, if I'm using both of those variables to try to explain why an individual is accepted into a select college, then there might be confounding that's going on, because both of those variables may be doing the same kind of job in terms of detecting like intelligence or something like that. So anyway, we have to always be worried about those confounding variables. Lurking variables are not considered in the study. Confounding variables are measured in the study. Both can confound the results of a study, so a researcher should be mindful of their potential existence. That is a big deal. So again, the difference between a lurking variable and a confounding variable is that a lurking variable is overlooked, right? It wasn't considered. But a confounding variable was considered, but it's just kind of doing the same job as another variable. So that could cause problems.